So we have this table again. We're going to work to put this into the calculator and then have it model my exponential regression for me. So if I run my calculator, I then, how do I get to the table to change it and put the values in? No, that's how I get to a table where it's going to spit me out values. I want the lists where I can just plug them in.
Oh, it's stat.
Stat takes me to my list menu, and I edit. So then I want 0, 5, 10, 15, 20. And I'm not clicking the buttons now, I'm typing them in. That's why you don't see me moving and clicking. Then I bump over to my next menu. I do 203, 177, 153, 137, 121, 111, and 104. Huh? No, it lets me type numbers on my keyboard, which is way faster than clicking up here because this click is slightly off. Here's the important part that a lot of us, like, this is where we hit our hiccup. How do I get to exponential regression? How do I get it to tell me my values? Well, if I go back to my stat menu and I go to calculate, right in the same menu where I went to edit my lists, I just bump over one. And in my calc menu, I go down to exponential regression. So you're clicking the same button to get to your lists as you are to get to your exponential regression. We just have one in the edit list, one in the calculate list. So I hit exponential regression, and I tell it I want list L1. Sorry, it did not pick up my second. Second L1, comma, you need a comma between your lists, second L2. Anybody having issues up to this point? We then hit enter, and it gives me the values that I'm going to use in my exponential regression. Now, however, the problem with this is the asymptote would not be at y equals 0. And to do a true, they're right here, Wyatt. To do a true exponential regression, we actually want to take 68 away from those values. So this is not my true exponential. Like, this would be the true exponential, but it's not the one that I want to use to model because I actually want to shift it. So what we're going to do is go back into the list, and this is all on your calculator showing, or on your notes. We go into L3. If I click, we're in step 2 right here. We want L3 to be L2 minus 68. So we tell L3, I want your list to be L2 minus 68. And it populates the list for me. Grant.
My calculator doesn't have a list 1. All it has is list 2 and 6.
You can just change your numbers. Like when you go to do exponential regression, you'll do list 2 and list 4 then. So add 1 essentially to each of your list numbers. Just shift it all over.
How do we get to the list?
No, I was just wondering if there was a way to put it back to list.
I would have to play with it for a minute.
No, like
It's in the menu somewhere.
Office, please, Haley.
So then I do my exponential regression again, but now I use L1, L3. Which for you would be L2, L4. So because I want an exponential that's going to show the asymptote on the 0. So watch what happens. Check these two lists. I'm going to now make a second stat plot. Just watch up here for a second. Second stat plot. I want to turn my first plot on. So I go in here, I turn it on, and I use list L1, L2 in the box. I'm good. I can go to my graph once I change my window. Again, we did this yesterday, making my minimum X 0. My max was like 40. Since I'm going to go for 30 minutes, I just go over it a little bit. I make my Y max 0, and I go to 220. And I make my scale 22. I can graph and see these points. But notice that asymptote is not going to be where I want it, really. I would like the asymptote to be at the 0 to make my life easier to work with, make the exponential function simpler. So that's why I now, second stat plot, make a new plot. So go down to plot 2, turn that plot on. But now instead of using L1, L3, or sorry, instead of using L1, L2, I now use L1, L3, which is my temperature shifted point. Because now instead of saying room temperature will be my asymptote, that 68, I want 0 to be my asymptote, so it looks like a true a true exponential. I'm going to change my symbol just because. And I can graph it. And see this one, that curve, would have an asymptote at 0. So if I model that exponential regression, I can go into my list again, go to calculate. Exponential regression is right down the list. And now that was my regression from L1, L2. If I use instead L1, L3, my new list of temps, this exponential regression is actually what I want to use to model that curve with the asymptote at 0. Now notice I can get this curve to match. What did I do to my temperatures to get list 3? What did I do to my temps? Minus 68. So how do I undo that? Plus 68. So now my exponential that I want to write is going to be y equals the 134.51, we round that somewhere, times, and of course I do parentheses, 0.956 to the x power. But because I had taken away 68, to get this where I want it to be, add your 68. Just shift it back up. Yeah. Go up. You have to, so when you go into the list, you have to move up. So watch, if I wanted to do that again, but on L4, I have to go up to highlight L4, then hit enter to edit what the list, this should start flashing down here where it says L4 equals, or in your case, L3 equals. And then you do second, whatever list you want to grab, say L3 minus whatever you want to take away from it. And then it'll make me a new list.
Oh, there you go.
So whenever you want to change the rule of the list, always go up to the list name and highlight on it. Any issues on getting this exponential regression? You should have tried to work through all of this so you know if you can or not. We good? So then when I put this in my y equals 134.51 parentheses, see, not all the hotkeys work.
Wait,
Pre-
I have a question.
Okay.
You can finish that first.
So then times 0.956. I don't know where that had come from. Then to the x power. When I graph this now, that curve would go through those points, but notice, because I forgot to add 68 to shift it up, so now when I add the 68, now that exponential shifts up to go through my original points. So now that will truly model my exponential. But notice if I did not use L1, L3 with the new asymptote value, I get the wrong equation for my exponential. I'm going to show you the wrong way to do this. Okay? This is the wrong way. Just pay attention for now. If I go in to my list, calculate, go down to my exponential regression, which actually is quicker to get to if you go up and cycle around the list, and I use my L1, L2, those original values, L1, L2. It gives me this as my exponential, 196.67. So if I wonder if it'll let me, probably not. I was going to capture it to take it up onto the other screen. If I use that, somebody just remember these values. We can probably do it pretty easy because that's 0.977, good enough. 196.65. 196.65. 0.997.
Or 2997.
Yeah, no, that's because my click is slightly off. Sorry. I don't know why that is, but this is an old emulator. To the x power. That's what it told me to use, right? I'm going to turn off my other graph just so we can see it. Is that the right line? Check my y equals 196.65 times the b value to the x. Well, what? Why doesn't this work at all? Because it's not the correct data. We need to model it with the asymptote at 0. That's how exponentials work. So if your asymptote is not at 0, we have to compensate somehow. So what we recognize is right here in my situation, if we kept going, this gets closer and closer to its like stopping point. Well, where would a temperature stop? It can't get colder than its surrounding area unless something else is doing it. So that's why we say, well, since room temperature is actually about 68 degrees and that's where it would stop, that's where my temps would level off, that's why I have to compensate. Does that make sense? Emily?
Okay, so I know why or where we got the values up there for the y equals 134.51 times whatever, but I don't know why you put them in that.
Because an exponential expression, and actually when I pull up this, it tells me your y, your equation, will equal the a value times the b value to the x power. So when and I wish this would let me second, if I do second entry and get my other, so this was the right one. So it tells me how to plug it into the equation.
Yeah.
And if I do other exponential models, it will tell me how to plug it into the equation. So because we know this is a regression, we use regression. That's where in the list, the calculate menu, you can have it tell you if it's a quadratic regression or cubic. You can make it like tell you whatever the formula is going to be. But you have to have the data to match or else it won't work out right. Any other questions from modeling this exponential? Try the got it on your own. We may only get through this one today. That's okay if that's what happens. Oh, well, that would be helpful. Are these the same values? They the same table values? So I go back to my list. 203, 177, 153. These are all the same values. So you should not have to change your lists. We should not have to change RL3. We just use that same quadratic regression. If that formula is still in your y equals, you can use the same thing, the same formula. You don't have to change it. All I need to do is go over to my table. But again, because my calculator totally reset, I have to go to table set. What do I have to do in my table set menu? Change independent to ask, so I determine the numbers. I go back into that table and say, okay, after 2 minutes, what's the temperature? But then y needs to pop up here. So that should be auto. I don't know why. Oh, I need to turn this on. That's what I goofed up. I turned off my graph so it won't give me y values if I turned it off. Always got to make sure that's highlighted. So now if I come to my table, well, there's 190. What about after 5 minutes? There's 175. What about after 11 minutes? Ooh, 150. What about after 20 minutes? Ooh, I'm getting closer. 22 minutes. 25. Well, I should have already known. It's going to be over 30, right? So the values that I'm using, I should have started with values over 30. I was waiting for somebody to point that out. If we know that at 30 minutes it's still 104, start with like 31. Close. 32. Oop, below it. So now try values in between. 31.1 or 32.4. What the heck, calculator? 31.1. Pretty close. 31.2. 31 point, we'll jump a little bit, 0.5. Very close.
For the homework, do we have to be like really exact? Because I was a little confused on number 13.
We'll talk about that in just a second. What's another way I could do this? If I'm looking for a y value equal to 100, instead of using my table and just guessing and looking for it, can anyone think of another way I could do this? Seth?
Can you switch dependent to ask?
No, I don't want my dependent to be. Well, okay, let's try that. What if I make my table set auto for my dependent, or auto for my independent, ask for my dependent, and now come over to my table and say, okay, if this is, did it keep that? It switched it back. No, auto ask. Yeah, this is what I want. It won't let me type anything in. It won't let your dependent be an ask because it's dependent.
Okay, then why does it have an ask? Why does it say ask?
There's a way to do this, but you can't do it in the table menu. Leon, do you know what I'm going to suggest?
Would it involve the the minimum and max?
Nope. Grant?
Could you just put it on the graph and then put the arrow over 100 on your graph?
Very close. Jacob?
Would you wait, couldn't you just invert that, flip that function around?
We could, but that'd still be a lot of work.
Is it possible?
Guys, what I'm looking for, this function models the temperature. I'm looking for a temperature of 100. So just set up another function that is the temperature of 100 and graph it. And what do I do now? Find the intersect. Sorry, I gotta take this. I think it's Vertical Adventures. Hello?
How's your day?
Hi, Carrie. How are you? Doing quite well. I'm actually in the middle of teaching a class. Is there any way I could call you back in about 20 minutes? I knew it was you, so I figured I had to pick up. But if I can get a number that's best to reach you at, I will call you back in just about 20 minutes. Perfect. Six 795 549. All right, I will call you back here shortly. Thank you very much. Bye. So notice that where that intersect point is took 33.19 minutes to get to exactly 100 degrees. What'd you get?
That's just your second curve. You haven't finished.
Oh, sorry. 31.91. My bad. Thank you for pointing that out. That was the value on my second curve. So guys, whenever you're looking for when y is a certain value, just throw another line on your graph and look for the intersection. That's way quicker than the guess and check method. Well, it depends on how good you are at quickly typing in numbers to guess, check, and get there. But this will be more precise. That's the other thing, is this is more accurate because you're not going to keep going to the 10,000ths place.
I got the same answer as you.
Do you get 31.910816?
Okay, no.
Okay, so who's more accurate?
Me.
No.
You might be more sassy, but you're not more accurate. All right, move on. Sorry, these got in the wrong order. Move on to question 4. This gets easier now. When we evaluate e's, this deals with logarithms. And you guys are going to get into logarithms in these higher order math classes. But logarithms use the value e. Now, e is a mathematical value. It's like pi. It's got a value. So first, type in your calculator e to the first power. Let's look at what is e.
Isn't e the one constant or
So second quit out of everything. We can second clear everything we have. If I do e to the first, notice e is a secondary button on ln. ln deals with logarithms. So I second hit my e to the first power. This is the constant value. It's named after, anyone know who it's named after? Euler. It's Euler's constant. E-U-L-E-R. Euler was a famous mathematician. So if you want to look up more about this, search up Euler's constant. But it's really important in certain branches of math. But when we're evaluating e functions, e to the third, real easy. put in e to the third power. Look, we got our answer. That's all we have to do to evaluate.
Why does it come out weird?
I literally just told you what e is Euler's constant. So if you want to, I don't really have the time to go deep into it, but if do you know it? I haven't looked at it enough recently to really.
It's like
That's not right.
So if you look at interest, like if you so say you get interest
Deals with
every,
compound.
Compound interest. If say you get interest every day, you would get more interest if you say you got half of that interest, but every half of a day. And then if you keep on doing that, then eventually it will just hit.
I'll try to find some materials about it because you guys are curious. It's because we use it inside of certain formulas. Like we've just like how pi, we use it with circles. The only reason that we use e is it makes things easier.
Oh wait, where's your last button? You need to press it.
Oh no, it got left on. That one takes too long. What's e to the 8th? Real quick. What'd you get, Seth? 2,980.957 and 987.
No.
So that is just work in the calculator.
In this problem, you will calculate continuously compounded interest. Suppose you won a contest at the start of 5th grade that deposited $3,000 in an account that pays 5% annual interest, compounded continuously. How much will you have in the account when you enter high school 4 years later? Express the answer to the nearest dollar.
Into an account paying 5% interest, compounded continuously. Has anyone heard of this whole idea of compounded continuously? Know really like what that actually means?
Oh, I know. It's kind of like math. I think we learned this in math 7.
We learned a little bit about compound interest, but we didn't do compounded continuously. Because that's harder.
Isn't it basically continually? Oh, it's just compound interest.
There's like. So the idea behind compounded continuously is there's no interest period. There's no point where your interest hits. It's just here's your percent interest, and we're going to compound all of it. And a lot of times when accounts are set up compounded continuously, is like if I'm going to take a loan and it's going to be continuously compounded, they run all the interest right now. They say your loan is for X amount of time. Car loans normally 5 years to 7 years, somewhere between 5 and 7 years. For a car loan. So when you buy the car, they say you owe for the car and your loan interest, you owe this much money. They tell you right up front, there's no way to really not pay that interest. Even if I pay quicker than what they want me to, the interest is pretty much already there.
Isn't this where you use e? Because like eventually you'll hit that point where you can't it just.
First, write the unknown is the amount A in the account after 4 years.
Yeah, so this is why we use E. And actually, I may have misspoken when I said it was Euler's constant. I'm fairly certain it is, but when I looked it up, that wasn't the result that it gave me. So I'm going to do some more digging tonight. But we use E, and by the way, so tomorrow you'll just be working on 14.2. I'll make a chalk talk for that. I'm glad I did not make a 14.3 chalk talk yet. So come into class, get a Chromebook, get your notes. Khan Academy, ever been on there?
Yeah.
He's got chalk talks.
Oh, I haven't.
So you see the chalk, you hear the talk. Is where that whole that's where it came from. That's all that you get is you see the chalk, you hear the talk.
Hey, Mr. Munson.
Yeah.
Just an idea. Maybe it didn't come up when you searched up Euler's constant because you put 2 L's and stuff.
Oh, yeah, maybe. So, this is a manipulation. Do you guys remember us using our Pertz formula, I equals PRT?
Yeah.
So, for simple interest, we had that as our Pertz formula. This is the real Pertz formula. Your account will have the principal times e to the power of rate times time. A is going to be equal. My power thing got really weird because my glitch on my smartboard. I've got like a line going across it that goofs it up. Yeah, I know. It shifts everything to the side. So that's our power, our little caret. So when we use this, all we do
Substitute
is
values for P, R, and T.
Initial amount, starting balance. So my principal is $3,000. What's my interest rate here? But that's not a rate, that's a percent. 0.05 is the rate. And then 4 years. Time has to be in years. Always when we're working financial math, time is in years. Financial math deals with long amounts of time. We always compute in years. Even if we have months, we just use fractions in 1/12, 3/12, 8/12, whatever it is. So we set up our formula, plug it into your calculator.
Now, use a calculator. Round.
And we will see that we get 3,000.
Now, grid your answer. 3,664.
Yeah, once you get your answer, A is like the account balance. So once you do the math,
use a calculator.
Once you punch it
round to the nearest dollar.
No, because that will not come out. That would be either...
the amount in the account after 4 years to the nearest dollar is $3,664.
For year, like we were dealing with how many cycles and how many interest periods. This is continuously compounded. There is no interest period. It's just happening all the time. So that's where the difference between compound interest that we did in 7th grade and continuously compounded, that's where their big difference comes into play. So try the got it. If you have an account that starts with $3,000, 5% interest, is this literally the exact same thing?
No, it's 4 years after high school.
Oh, yeah, there you go. So if you get it in 5th grade and we're going to 4 years, no, after 4 years of high school, so at the end of, essentially when you're going to college, how much money are you going to have? So start at 5th grade. So we get 5th grade, 6th grade, 7th grade, 8th grade, then all of your high school, how many years? 8. So our formula here, our account, A really stands for account balance, is going to be P times E to the RT. That's going to be $3,000 times E to the 0.05 times 8. You already finished this grade? What do we get? $4,000 what? I got 4,475.
That's what I said.
Okay, sorry, I thought you said 65. If you type this in correctly, that should be what you get. Now be careful, when you put this in your calculator, it opens a parentheses for you. So in that parentheses, you want to just put the 0.05 times the 8, then close your parentheses. Yeah, do not close the parentheses until you have typed in the multiplication already. Cool on solving that? Good luck, man. We need some clotting factor. They make this stuff now that's super expanding, like cotton gauze type stuff, that they can put into a bullet wound and it will expand and close the wound.
That's Okay, cool.
that they can
You
like
already-
these little pellets expand to like way big, like can potentially expand to like 100 times their size or something crazy. So yeah, they're able to fill a bullet wound.
Fill someone's car.
I need some of those.
All right.
Those at the
Yes.
Dollar Tree already.
Yeah, but it's the military grade stuff is a little better. So the function p equals 80 times the value of 1.25 to the d models the population of a city in thousands. Always pay attention that this is now number of thousands. D decades after some event. Maybe there was a bomb explosion and the city's rebuilding. Maybe, you know, there was a zombie outbreak and the population is decreasing. Who knows?
Well, Marty,
What?
We stay the same because they're still populated. They're still populated
Set.
zombies.
no.
What exponential function will model this? I forget what I put in your guys' notes. So if D is decades, and you can see this in your notes, but if D is decades, and I want to put this into an exponential form for an exponential function, I really want a power that involves time in years. So what I'm going to do is say that every year is actually going to be a tenth of my power that I originally had. So I can take my 1.25 to a decade and change decade to 1/10 t. And then I can actually apply that power because this is what I set up to convert out, that 10d. I think they may have actually written this a little incorrect.
Yeah, because 10 years equal 1 decade, not 10 decades equal 1 year.
Yeah. I think this is actually slightly off. Let's skip straight to the got it. Ignore this guy for now. I think that one's messed up.
Wyatt, stop talking.
Let me see if they fixed it in the new stuff. Because they updated things over the summer. So guys, that's the kind of stuff that really makes me question your maturity.
Wait, what maturity?
Correct.
I'm pretty sure he knows that.
No, I'm
They have the same solution here. There are 10 years in a decade. Oh, that okay. So this is right. Sorry, it's just how you think about it. So, 10 times the number of decades will be the number of years. So this is, yes, 10 years equals 1 decade, but the problem is we want to say, how does D relate to T? Well, 10 times the D value, say they said 2 decades, 10 times that value will give me the number of years. So that's how we set up that D is 1/10 T. Not that a decade is a tenth of a year, but that the value D we're using equals 1/10 T. Because 10 times the value of D will equal T, we manipulate the equation and we get D is 1/10 T. Does that make sense why we're using that? Because it threw me off for a second. So if you're still confused, let me know. So then we apply the power that we can apply. So we take 1.25 to the 1/10 power, get my new base value, and I now have this in the form of y equals a times, or y equals a times b to the x. A is my 80, b is my 1.023. Questions on this? Because it was kind of weird at first. Because then we get The answer is about 2.3%, because if this 100% is the initial population, are we exponential growth or exponential decay? Are we gaining population, losing population? If I'm over 100%, I'm gaining. So I'm gaining by about 2.3% per year. So before we get out of here, let's try the got it together. So we set up the same thing. Except again, we want to say that 10 times the number of decades will equal the number of years. Therefore, D is equal to 1/10 T. So remember, this is in thousands. So that's why we're using 110 to represent 110,000. We just take off the extra zeros to make my life easier to work with. I then have 110 times, well, what is 1.16 to the 10th power? 1.0149536. Yeah, right. So if we round that, 1.0149, or we could really round that up to 1.5. If we look at the growth percent here, we'll move this over 2 places to look at the percent. This is really 101.5%. So my growth percentage is about how much? Yeah, I have a growth percentage of about 1.5% growth every year. If I wanted to look at the growth per decade, I get about 16% growth in a decade. But that comes out to approximately 1.5% each year. So you have no new homework. I'll shift today, like the 14th, I'll shift that homework to tomorrow. You will have a chalk talk when you come in. The notes are already back from the copy center. The homework's already back from the copy center. Guest teacher will have all of your materials. Just come in, get a Chromebook, get to work. Please bring your headphones if you have your own. Thank you very much, guys. Huh? Is it the same one you've had? It's what? 2. You brought back the other ones, right?
Oh, yeah, yeah.